Hi, I'm Professor Goins, and in this video I'm going to discuss how to find the equation of a line in space. So find the equation of the line in space, in other words R3. Generally, when I say space and R3 are generally interchangeable, which is parallel to a given vector and passes through a specific point. So I'm going to do this generally first to get the formula that we're going to work with. And again, it's parallel to a vector v, which a vector is only determined by its length and initial point, or its length and direction. So we can take any vector and we can just equivalently pop it at the origin, or put its initial point at the origin. So I want it to pass through this point here, ABC, and I'm going to find the equation of the line that's parallel and pass through this point. So that'd be the equation of that dotted line. And the way I'm going to do that is I'm going to use a variety of vector arithmetic operations. The way I'm going to construct this is I want to find how could I incorporate this point P, which is x, y, z, which could lie anywhere on this line. How can I get the equation that would have this line with this point and this point on it? All right, well, let's start with a couple things that we know. I would have this vector here, and I know this vector here, which starts at the origin and lands at that point there. So that'd be the vector, let's label that R naught. And my goal is to find, so let's put in the vector that we're ultimately trying to find and figure out how we can find it. So I want to find the vector that lands at this point here. So that would be that vector right there, that black one. So this would be the vector R of t, or let's just abbreviate it as R for the moment. Okay, so the way I'm going to do this is I'm going to have to figure out what vectors can I add to get this one. I have the purple vector, the R naught, I've got the vector V, and I'm going to have to somehow combine those to get the black vector. If you remember the parallelogram law from a previous video, the parallelogram law says the following. So let me do this off to the side. If I have two vectors, let's say I've got this vector right here, and I've got this vector right here. The way we add those is by taking the line segment that starts at the tip of this vector and is parallel to this one. And then I take the line segment that is parallel to this vector but starts at the tip of this vector. So those are parallel, and then to add them geometrically, we go to this intersection point and we go to the common initial point, and that would get that blue vector there. So I'm going to use that idea, the parallelogram law, to somehow combine these two. Now if I add them as is, in order to not mess my picture up too much, if I take this line segment and I take the line segment from here, this would be parallel to the purple one, and that would continue out, say, to here, because I would take this line segment. So that means if I add them together, I would get the vector that terminates here. My arm's, of course, in the way. I'll get the vector that ends here. But I want it to go up to there. So what I'm going to do is I'm actually going to stretch this one out a little bit. And remember that we can stretch a vector by multiplying by a constant. Certainly if I were to double it, let's see, let's pretend this is the same length of v. If I multiply this by 2, it goes up to here. And then if I were to add this vector and that vector, it would come up to here. So that's pretty close. So it looks like I have to go a little bit farther than that. And in order to get a relatively accurate picture, I'm going to start by cheating, meaning I'm going to put in the vectors that I'd have to add. This purple one, and then I would have to have this stretched out to, let's see, I'm going to probably have to get in the way of the camera for a moment. Actually, let me try and do it over here. How high up would I have to go? Okay, and then if I want to add that purple vector, so parallel to that, it would have to go okay. So it looks like if I take this red vector here, And let's see, what color should I use? Let's use a black. Let's use purple. I take this vector, this red vector, and I stretch it along the squeaky whiteboard up to here. So this would be a constant multiple of v. And then I take this stretched v with this r naught, I add those two together. You can see using the parallelogram law that I'm going to end up with that vector r. Okay. So the summary is the following. The vector r is given by the initial vector plus t times v. So this right here is the formula for the equation of a line in 3 space. Okay. Notice, so this is a fixed vector, this is a fixed vector. The only thing that changes is t. And like I mentioned before, if I were to just double it, that would put me to about here, and that would generate this point. If I triple it, that would put me up to about here, that would give me this point. But t can run through any real number, which means I can generate any point on this line. Okay. So let's start by, let's do a couple examples. First example, find the equation of the line in R3 passing through the points 1, 2, 5, and 3, negative 1, 2. If I look at the equation that I have in this box, there's 2 things we have to find for any one of these, right? T is a variable, so I have to know r naught and I have to know v. V is going to be the vector that's parallel to the line, and r naught is going to be this fixed vector that attaches to a specific point that we know on the line. Okay. So let's start by just kind of a motivating idea here. Let's say that this point right here is 1, 2, 5. Let's say that this point right here is 3, negative 1, 2. And we know that, so let's say this is the equation of the line that we're trying to find, and it contains those 2 points. Well, if I think of what we did over here, I know that this line is parallel to the vector v. Okay? And I know that one of the vectors that I'm going to use is from the origin up to this point. So let's say I'm going to use this vector right here. So let's say this is our vector r naught. Well, I don't have this vector v though. But what I do have is this vector that lies on the line. A vector that lies on the line, of course, is parallel to the line. So I could take this vector here and use that for my vector v. Okay, so let's write down the vectors that we know. R naught is going to be the vector that terminates at the point 1, 2, 5. The vector v is going to be the vector that starts here and ends here. So remember, the way we find a vector between 2 points is I subtract corresponding components. So it's terminal minus initial. So 3 minus 1, negative 1 minus 2, and then 2 minus 5. So this would be the vector 2, negative 3, negative 3. So this is my vector v. And then you take both of those and I substitute them into this general equation that we have up top to get my equation of the line. So therefore I have r of t is going to be the vector 1, 2, 5 plus t times the vector 2, negative 3, negative 3. And we could leave it in that form, but to show you something that will tie into the next example, what I'm going to do is use just a property of vector arithmetic where I can take this constant term. Well, it's a variable, but it's plays the role of a scalar when I distribute it through, and distribute it through to that vector, and then I add this vector. So again, to distribute this through, we multiply each component by this, and then when we add vectors, we add corresponding components, which gives me the following. So this would be 1 plus 2t, 2 minus 3t, and then 5 minus 3t. Notice that each component of that looks sort of like the form of the equation of a line that you learned in your algebra class, where, remember, we have y equals mx plus b, where m is your slope, b is your constant. Well, I could equivalently write this as b plus mx. Actually, let's write it as b plus xm. And so this is a constant plus a variable times a constant. Well, that's what each one of these are, a constant plus a constant times a variable. Oh, I guess I could have left that as mx. Constant plus constant times a variable. At any rate, so that's how you find the equation of a line in 3 space. Let me clean up the left side of the whiteboard, and let's do one more example. Okay, find the equation of the line in R3 passing through this specific point and parallel to this other line. So let's see, what information do we have? What information was given? What do we need to find? Okay, so I've got a point that it passes through, and remember that we can use that to generate our R naught, right? So it's just a vector that's going to terminate at this point, and it's parallel to this line. Well, the only other thing that I need to find is my V, right? I know R naught, I need to find V. In the previous one, we found V by just taking the vector that's between these 2 points, which of course the line segment and therefore the vector between 2 points lies on the line. So what I'm going to do is, let's look at this previous example and see, work it backwards and see another way that we could find V, because of course V has to be embedded in here, right? Because it's part of the equation, so it's part of this equation. Well, if I look where V was 2, negative 3, negative 3. Notice that that was the part that I multiplied through by t, and then I added the 2 vectors together. So really what I'm going to ultimately do is take this last step, which is analogous to this, and let's work it backwards to find our V. So I can separate S as follows. This would be 0, 1, 2, plus 2t, t, minus 4t, and then I can factor a t out, So that would be 0, 1, 2 for the initial vector for s, plus t times 2, 1, negative 4. So for the vector s, that's the vector v. And since I'm trying to find the equation of the line that's parallel to this, they're both going to be parallel to v, and so I can use this for the line that I'm trying to find. Okay, so if we plug those things in, the vector r of t, so r naught plus tv, would be the vector 4, negative 5, 1, plus t times the vector 2, 1, negative 4. And then I can distribute t through this vector using scalar multiplication, and then I can add the components of the corresponding components of these two vectors. So that'll give me 4 plus 2t, negative 5 plus t, and 1 minus 4t. So this right here would be the vector, the vector equation of the line, which would be parallel to this one and would pass through that specific point.